Oh, so glad to see this wonderful group. It is such a pleasure to see all of these beautiful people here today. Thank you for being here. And we have a lot packed in during this short session, three quick sessions. We're going to hear from two of our sponsors, and then we're going to do some overview talking about the conference itself. So without any further ado, let me introduce our first speaker of the general speaker of the conference. Vincent Vanhoucke is a researcher in charge of Google Brain. He has done his undergraduate degree in France at Polytechnique and what? Central. Okay, Central. And then did a PhD at Stanford. He has been leading research at Google and has been really at the forefront of robot learning. And I think it's really important to also point out that this whole conference was really his idea. So big round of applause for that. Yeah. All right, I don't think I could say anything to top that. So, okay, all yours, Vincent.
All right. Well, thank you, Ken. And yeah, I actually wanted to start on this and really express my deep gratitude for every one of you being here today. You know, we started the conference 6 years ago already with this idea that, you know, maybe there is a bunch of people in machine learning who like robotics and a bunch of people in robotics who like machine learning. And maybe if we put all 20 of them in a room, we'll have a nice symposium of sorts. And this blossomed into a really amazing community that I've loved to be part of for the past 6 years. So thank you for being here. Thank you for being wonderful in so many ways. It's a really fun community to be part of, very inclusive, very open. You know, lots of sharing going on, and it's always wonderful to be here. So thank you. I wanted to talk to you about all the things that we've been working on at Google over the past year or so. A lot of the focus. That's not my slide. Let's see if it's a lag in the system. Oh yeah, that's my slide. A lot of our focus at Google has been to try and understand how do we enable robots to basically assist in the real world at all sorts of tasks, particularly tasks that involve helping people, manipulation, physical assistance, and trying to understand how could we bring robots to really be helpful in everyday environments. So you'll hear from a lot of my colleagues talking about a lot of those aspects in the next few days. I highly recommend the keynote that my esteemed colleague Sandra Frost will be giving on Sunday about scalable autonomy. This will be fantastic. We've got two talks, one on large language models, one on ping pong. So what's not to love? And then a number of poster sessions, and including poster sessions with some of our collaborators at various universities that we've been working with. So please don't miss any of them. What I wanted to focus on a little bit is some of the themes that we've been particularly excited in the past few months. Yes, we fell into the large language model rabbit hole like many people recently. And I have to say, I regret nothing. It has turned out to be, you know, what could have been a gimmick of, you know, bringing language models and robotics together, smashing them and publishing a few papers, has turned out to be a fantastic line of inspection and very bringing new ideas to the table, and has been a lot deeper than could have been anticipated on the surface. So you'll see a number of projects around that theme here at CoRL this week. There's a SECAN, the work on code as policies and inner monologue that are being presented. Another line of work has been this interactive language work, where it's about being able to talk to robots in using an open vocabulary language and have it control it in real time at the very low level. And what's interesting about that work is that it's actually trained entirely end-to-end using hindsight relabeling in a very, very scalable manner. And it's giving us very nice results. We also have some very nice work on sort of scene understanding that's queryable using natural language with the NLMAP SECAN work. So lots of cool stuff in that vein. I feel like this area of enabling robots to interact using natural language is really blossoming in a good way, and in a way supporting a lot of the rest of the research that's happening in the field in novel ways. Another focus of ours has been learning in complex and agile behaviors. So there will be talk about the ISIN to real work later at CoRL. We've been doing a lot of work on legged locomotion as well. I'm just highlighting this work on PyRAS using predictive information. And I think Sandra is going to talk a lot more about it during her keynote as well. But one thing I thought I would do today is talk about something a little new that I'm particularly excited about. This is basically on this long journey of trying to figure out how do we build the most efficient data sponge or data representation for visimeter control. How do we go from pixels to actions in a way that's trainable and learnable in the most efficient way, right? So we need models that are going to be robust, that are going to generalize well. If we go at it naively, possibly if we want to train a large language model, it might not be fast enough. And so we have to take into account the fact that a robot has to be, operating in real time. And then there's the question of what kind of data do we give to the robots to train it, and at what scale do we need to operate, and what level of diversity of the data does matter. So we've been working on this project called RT1. The base of it has been, we've been collecting a lot of data. I hope it renders relatively well on the video, but basically collecting a lot of interaction data with mobile platform robots on tabletop environments, doing all sorts of various tasks in those environments, and trying to explore basically, if we have a very large sample of data, how do we represent it best, and can we actually turn that into an effective visimeter control policy? The architecture we landed on, which should show up momentarily, maybe, if I'm lucky. Let me try again. Yes. We'll solve robotics before we solve AV. So the architecture we landed on is what we call this Robotics Transformer, which basically takes as an input natural language instructions that are all tokenized, takes as an input a collection of images that are also tokenized. And the way we do the tokenization for images is an efficient net sort of backbone, and then with film layers that enable you to condition that on the natural language inputs. And then a component that's called a token learner. That's a prior work from my colleague, Michael Ryu and his collaborators, that enables us to compress that tokenized representation by about 10x. So we start basically for each input with about 80 different tokens and compress them down to 8 tokens that are then input to the transformer to make the entire pipeline very efficient. So we have a big transformer model that actually just simply predicts tokenized actions. They're not, the action representation is not particularly clever. It's just quantized along all the dimensions of the action space. And so we've trained this on a pretty large corpus, 130,000 episodes collected by 13 different robots over the last year and a half. We train them to perform a variety of tasks. So I know the T word is very controversial in robotics. Defining a task is always a kind of an art. There is no sort of common definition of things. Think of it as really short horizon tasks, and each task is just a different combination of an action and an object. And the results are really nice. So what we're seeing is that for the first time, I think in my experience, trying to train models like this, we can entirely, I want to say overfit, but like we can get almost 100% on the kind of tasks that we had trained the robot on. So there is generalization since it's different instances of the same task by a robot in real world. But if you will, in the closed set of all the tasks that we had provided data for, we basically can get to 97% performance. And that's the first time that I see a model basically being able to completely nail the problem and then generalize and not overfit to it. So on unseen tasks, when we had distractors, when we had backgrounds, the performance is still very good and generalizes as well. So that makes me really hopeful that iterating on this kind of approach will enable us to build models that generalize well, that consume a lot of data, and are able to sort of improve themselves using that data without any saturation, basically. So we've also applied this to more long horizon tasks, right? So when you have a long horizon task, the likelihood of success goes down if any of the different subtasks fails. And we actually are able to get very good high-level execution performance by combining the model and putting under the SECAN work, which will be presented later in the conference. So I won't talk too much about this, but it's starting to feel like there is actually a very good lift, even on very complex tasks that involve those kinds of primitives. One thing that has been most instructive from this exercise has been to look at how the data scales with and how the performance scales with the data that we provide. So obviously, if you just reduce the amount of data that you throw at the problem, performance is going to get worse. And whether it's on scene task or in generalization, you see there's definitely a downward trend. But if you do the following, you take all the tasks that have the least amount of data in your data sets and you just remove those. You end up in a place where you remove very little data in terms of volume from the entire data sets, but you decrease the amount of the task diversity by a lot. Here we removed 25% of task diversity. And the drop in performance is really marked. It is really, really significant. And so that really, really suggests that if we want to be successful, this multitask setting and this really broad diversity of tasks is actually very important in achieving very good generalization and a lot of robustness. And conflating just data size and data diversity is often what we see. We have a lot of, random data that we throw at the problem, but actually focusing on diversity might be a lot more important than just focusing on raw data sizes. The model is also pre-trained using sort of just visual data, so there's a lot of the visual components are already, the visual primitives, if you will, are already learned independently. Another set of experiments that we've done is looking at how different embodiments kind of affect the model. So right now, we train on data that's collected on this robots from everyday robots, and then we evaluate on those robots in match condition. And we also did add simulated data. And the process that we have is we have a simulator of the robots. We have a sim-to-real process that maps using a variation around cycle gain to realistic looking images, and we can augment the data set with that data. And in particular, we can augment the data set with objects that have never been seen in the real world, that have only been seen in simulation. And when we do that, we get much better performance on the objects that have only been seen in simulation, even when we evaluate them in the real world. But more importantly, we also see improved performance on those objects for tasks that have never been seen in simulation. Right, so that means that we don't have to instrument every possible task necessarily in simulation. We can limit ourselves to very simple tasks in the sim environment where we actually have to script them or provide demonstrations for them. But we can hope that there is a combinatorial effect of the skills and the objects being kind of relatively independent from each other, and being able to leverage each other to improve performance. So I think that that's a very interesting direction. The other really interesting thing is, well, we had a lot of data that was lying around from a completely different setup. It's a KUKA arm doing bin picking that we were using in our previous work on multitask. So we just threw all that data into the model and just to look at what happened. And again, the performance on the real eval did not degrade by any significant amounts, but the performance on the bin picking evaluations of pre-training the model, if you will, on this data from a completely different morphology and different set of tasks actually improved quite a bit. And so we are, we get a lot of benefit from pre-training from a very large model, potentially, even if the morphology of the system is not matched. And that's intriguing because that's kind of suggesting that, actually building those large models across morphologies has some clear benefits. And we can finally hope to start building models that are not, dependent on exactly the robot you have in the one lab that you have, and we might be able to train models across the community. Why not? So this is there's a lot more about this work. You can look it up on the web at roboticstransformer.github.io. It's work by a lot of my wonderful colleagues, and that I want to really give a shout out to, because this is really the kind of work that takes a village to accomplish. So just to recap, transformers are great. They're really amazing machines at sucking up data and extracting meaning out of them. Scale matters, yes. Diversity matters more. And so that might impact how we think about robotics. And I think in the context of having, for example, language condition models, where the diversity of tasks that can be expressed by language is actually a lot bigger than the diversity that it would get from building a bespoke setup for a single robot, that might really inform how we reason about how we build policies for robots in general. And then maybe we're inching towards actually building something like a foundation model for robotics. I don't want to claim victory in that direction yet. I think we're very early in the process, and there's a lot of questions that we need to answer in terms of scale, in terms of data representation, in terms of lots of things. But this gives me hope that we can get in this, we can make progress in this direction. It's actually a productive direction for us to be investigating. That's all I had. If you're interested, if you're a student and you're interested in talking to us, feel free to reach out to this email address, and then I'll take any questions. Thank you. Any questions, sir?
So I like where you put that T word, the task.
Yes.
Back to that. because a lot of the tasks that you're showing are these sort of tabletop moving object A and moving object B, sort of positioning range. Can you say a little more about how? Oh, thanks. Can you say a little more, Vincent? Thank you for this, and I think we're all really appreciate the way Google has pushed this envelope and in scaling. And so I'm just wondering about how you're thinking about tasks more broadly, and is it also, do you think that these will generalize to, let's say, industrial tasks or surgical tasks or tasks that are in very different environments?
Yeah, that's a really good question. If you look at the space of tasks that we've defined here or that we've trained on, at the end of the day, you've got, pick, place, knock over, knock back up, open a drawer, close a drawer, very, very simple tasks in the sense like there is not a lot of dexterity to them. There is not a lot of complexity to the actual manipulation. And so it's a benchmark. It's not the whole world of robotics, and it's not the whole world of what we would want to apply those kinds of models to. And so there is an open question of, can we actually do this in a more dexterous setting, in a more, where precision is more required? And that's, I think, is something for this community to find out. I don't have the answers yet. And it would be really interesting to start looking at applying those kinds of approaches in a completely different setting.
So one question from me: in the RT1 model, you stacked a bunch of images and connected them to language. What do you expect is the value of an intermediate 3D representation potentially that is being reconstructed or modeled? In RT1 model, you stacked images and you added language conditioning as well. Do you feel there is value for intermediate 3D representations in the model? What would that bring, or is this necessary?
3D would be fantastic. Yes, I think if
you
we
also
can,
enable the video there.
so in the back of my mind, I always have this idea that the real visual representation we should have at the core should be 3D in some ways. And I've been very disappointed at many of the sort of 3D sensing technologies we have out there, like depth cameras and things like this. I think I don't particularly like any of them, and wish we had better ways of extracting directly 3D information that would be practical from a sort of geometric standpoint and from a practical standpoint. I have a hunch that if instead of we doing things in the pixel plane, we did things in the real world frame and operated directly on 3D representations, we would simplify a lot of our headaches.
So maybe there is area for autonomous vehicles where I work, and this domains to cross-pollinate, because there's some interesting developments in our space with unsupervised 3D reconstructions and so on.
Yeah, I think this is ripe for also really a market change in how we approach 3D. The new approaches like NERF to do implicit representations of 3D just from very simple sensors. I'm really excited about that. I think there is a potential for some new things to happen there, and the fact that a lot of those things are also differentiable and can be brought into the pipeline seamlessly is very exciting. Death to the point clouds.
Thanks for the great talk. I have a question regarding this foundational model. So you said that you used previous data from the KUKA. So can you give more insights on how you do that? Because I was imagining, how can we use and leverage old sensor data where we have old sensor models, and now we have new innovations in sensor techniques and also multiple modalities. So how can we integrate all these learned knowledge in these past data sets?
Yeah, so the nice thing about, if you have lots of data that's just images and you have a common encoder, you can obviously just throw them into the model and hope that the model will generalize. What's less obvious is how do you merge different different data that has different action representation, for example. In this case, we do nothing. We just have different tokens, action tokens for the different action representations that are non-overlapping, and just throw them into the model and have them predict the different modalities. So no smarts whatsoever. Obviously, leaving as an exercise to the transformer to find any commonality between the different action representations, if there is any, but there is no inductive bias that pushes it towards it. And that's actually a very interesting research question of how would we provide an inductive bias or an action representation that's common enough across different embodiments that we would hope to have transfer happen from them.
Okay, let's thank